All right, welcome back. What we're going to do in this video is I'm going to show you, we're going to go through some of the boundary conditions that we're going to be using. And we'll use these not only in this course, but in 303 as well later on when we get into some of the beam, the moment and bending lectures. I'm going to go through the boundary conditions, and I'm going to go through an example of how we actually come up with this and show you kind of the process. So last video was the proof, this video is the process. So boundary conditions, we know that we need them to solve for the constants when we integrate, right? We talked about that when I talked about differential equations, because every time we integrate, if we do the general solution, we have the integral of y by dx is equal to 1/2 of y squared plus c. So we need to be able to solve that constant. And we do that through boundary conditions. So when we're talking about civil engineering, what we're going to do is I'm going to give you a bunch of the different boundary conditions that we will actually use. If we consider this beam in the xy plane, I'm going to kind of break it down into 4 chunks. So we're just going to talk about the first chunk there, this one, and that one. And I'm just talking in generalities about what they are. So just remember when we're talking about the derivatives that our fourth derivative is related to a uniformly distributed load. The third derivative is shear, second is moment, the first is angle of rotation, and the y is just relating to the deformation. So if we look at region 1, we're talking about just the support itself. So boundary conditions based on the support. And the boundary conditions that we come up with are based on real world conditions. So in the case of a simple support, it doesn't matter whether it's a roller or a pin, as long as it's at the end. So when we talk about simply supported beams, right, it's supported at both ends, right? So as long as it's a support at the end, then it's considered a simple support. Boundary conditions that we can use there, and it doesn't matter where it is. So we have one, this is x equals 0, and then we'll have x equals L over here. But as long as the support is simple, we can say that at the value of x, my second derivative of y is equal to 0, and my y is equal to 0. Well, if we look at what those relate to in the real world, my moment is equal to 0, and so this is the same as saying moment, and this is the same as saying my deflection. Now the deflection is equal to 0 because it's where the support is. There's no deflection of the beam where it's actually being supported. That makes sense. When we think about the moment, because it can't resist moment, then when we draw our bending moment diagrams, if it was loaded in the center, it's going to look something like this, and we know that our moment is 0 at either end, right? So those are the boundary conditions we can use for region 1, that simply supported region. Boundary conditions that we can derive at the point load at region 2 are a little bit different. And we're going to go down and see what those are. If we have a concentrated or a point load, then we can say that I'm going to draw it over here. The deformation, if we're coming in from the left-hand side, is going to be exactly the same as the deformation coming in from the right-hand side. And all that is to say is that y is equal to YL, which is equal to YR. The same can be said for the slope of the deformation, which is the angle of rotation. And the same can be said from the moment, because we don't have any discontinuities, right? When we draw our shear force diagrams and our bending moment diagrams, we know that we don't have any discontinuities. There's no break in the moment. So it doesn't go moment and then nothing and then more moment. It just continues. It has to be continuous. So that is another one that we can use. And then we also get that if we take the shear from the left and the shear from the right and take it away from each other, then we're going to get that it's equal to P over the stiffness, or that load P. And we can look at that through the shear force diagram, where this is P, right? So this is the shear on the left-hand side, and this is the shear on the right-hand side. And the difference between them is that concentrated load. So those are some boundary conditions we can use there. The interior support, so point 3, and that's just any support. Again, it could be a pin or a roller as long as it's not on the ends, has different boundary conditions. So in this case, the interior support has that the double prime, or the moment, on the left-hand side is equal to the right-hand side, which is fine. That makes sense. It's kind of the same principles that we talked about here. The angle of twist on either end has to be equal. and that's makes sense as well because again we don't have any discontinuities. But then what we get is, because it's a support, there is no deformation. So if we have something that looks like this, like we have in our diagram, and we're loading it, doesn't matter which way we're loading it. If we load it there, the deformation will look like this, right? So there's going to be a y here, and there's going to be a y here, but the actual, so it doesn't matter which side we come at it from, YL and YR, they're going to be equal to 0 because it's on a support. And we'll get to how to use that in a bit. And finally, the cantilever end, so this portion out here, what we get is that the second derivative, or the moment, is equal to 0, and that the first derivative, or the angle of twist, is actually going to be equal to 0 because there's no moment, right? So if you take the derivative of 0, you still get 0. And why that is basically, so if we look at this scenario, and we have this is P, say this is L, and this is, it doesn't matter, we'll call it X, even though I don't really like using that. And we solve for the constants, right? If these are L over 2, or we solve for these reaction forces, that'll be P over 2, that'll be P over 2. We draw our shear force diagram. It's still going to look like that, but now there's going to be nothing in here, right? Because if it's P over 2, this is P over 2, it's positive and negative. And then we draw our bending moment diagram. It's just going to look like that, and there's going to be a region of 0 bending here. So if it's 0 on both sides, then it's the cantilever, or then it's the second derivative and the first derivative are equal to 0. Yeah, we'll get to the rest of that in a minute. The only other boundary condition that we have to talk about, that we haven't talked about, is if we have a cantilever support. So if it's fixed at one end. I guess fixed support would be a better term, right? So a fixed support resists in the X and the Y, and it also resists moment. So what we can get for the cantilever beam is that our Y is equal to 0, right? Our displacement is equal to 0 because it's fixed. But we also get that our angle of twist is equal to 0. So even if we load this beam out here, eventually by the time we get to the ends, the deformation will look like this. Right, so we're going to have a y max at the end, or wherever, yeah, it'll be at the end. But at this point, right when we start, if we talk about it in very, very small versions, there's not going to be any angle of twist because there's no, because it's resisting moment. So that moment there is going to make sure that there's no angle of twist there. And that's all, that you just kind of need to understand that with the cantilever beams. So with those boundary conditions, we can basically use them to solve for a beam given any number of loading conditions. What we're going to do now is just go through an example using a very simple beam, and I'll show you how to do a little bit more complex ones in later lectures. But right now we're just going to go through using this beam. We've seen this beam already, and basically it's a uniformly distributed beam of length L that's simply supported. So we're going to use the important concept that we developed earlier, that the fourth derivative of the deformation, our fourth derivative of y, times the stiffness is equal to our negative q, so our loading. That's since it's a fourth order non-homogeneous, it's not homogeneous because we have the q here and it's not equal to 0. We're going to have a solution in the form of a particular solution and then our complementary solution, and then we're going to add them together to form our complete solution. So what we're going to do is we're going to go back to the steps that we learned for differential equations, and we're going to start and make it a homogeneous equation. So that'll give us the complementary equation is our homogeneous version. We're just going to get rid of that negative q. Then we're going to solve for that. So if we assume the solution, a solution of y equals e to the mx, it'll be plus c, for our solution to that homogeneous equation, what we need, because we have fourth order, is we're going to have 4 versions of that solution. So when we did the second order homogeneous solutions, remember we had e to the mx times n squared plus a times n squared plus b times n plus c equals 0, and then we solve for the roots. Because it was a second order differential equation, there were two roots, or two solutions. Because we have a fourth order equation, we're going to get 4 solutions to this problem. So what it looks like is that the complementary solution is that we assumed this, and what we're going to do is we're just going to say that it's e to the mx times those constants and then different versions of x. So when we take the derivatives of it, we're going to end up equaling 0. So this, if we expanded this, I mean, I don't know if it's worth doing, but e to the mx of c1 plus c2 x e to the mx plus c3 x squared e to the mx plus c4 e, or x to the cubed e to the mx. So when we take the derivatives of those, we're basically going to end up with y equals 0, right? Because that's how we come up with the solution. If we assume that the e to the to the mx is not equal to 0, then we can just kind of put that one aside for now, because we know the solution comes in the form of e to the mx. But we also know that what we're going to do is take this kind of solution. So we're going to use those constants times their x values and solve for x in this case. And that'll give us our solutions the same way that when we had two roots, we just solved for the roots, and that gave us our solution. So I'm just going to write it in this form for now, and that's fine, because I know that that works. Then I'm also going to assume that the particular solution, so the solution to this actual equation, is going to be in the same form. So it'll be y is equal to e to the mx times c5 plus x to the fourth, or times x to the fourth. So it's not the same as any of these, so there's no x version there. There's x there, there's x squared, there's x to the third, and there's x to the fourth. So I've assumed that that's the form of the equation. This is all you need to know, is that we're going to assume this kind of the form of this equation. We're always going to assume it to be this case. So when we write the total solution, actually there should be a yp. If we write the total solution, then we're going to get that y is equal to the particular plus the complementary solution, and the whole thing equals this. If we take the derivative of that 4 times, what we end up with is that y prime is equal to that, y double prime is that, y triple prime is that, and y to the 4th prime is equal to that. Now, if we go back to the beginning where we said y to the 4th prime times the stiffness is equal to negative q, q is a known, we can rearrange that equation to state that we can rearrange this equation and then use it, plug it back into here. So y to the 4th prime is just simply equal to, so y to the 4th prime is equal to q, negative q over the stiffness. And then we put that into, it equals 24c, c5, and we get that c5 is equal to negative q minus 24 ei. So that means that our particular solution works. And it also, it's something we've solved for one of the constants, right? And all we've done is solve for one of the constants because we would know our q value, and then we just end up solving for the equation. If we look at the beam itself, we need to come up with boundary conditions to solve for the rest. So we've solved for C5. Now we need to come up with boundary conditions to solve for C4, C3, C2, and C1 in order to make our solution work. So if we look at the beam and we think back to where I just went over with the boundary conditions, in just using that property, too many arrows, I'm going to skip across. If we use the property where the 4th derivative times the stiffness is equal to the negative of the load, this is technically one of our first boundary conditions. If we go back and look at the simple supports, remember with the simple support, the boundary conditions for simple support were that y double prime is equal to 0, so our moment is equal to 0, and that y is equal to 0 because our deflection is equal to 0 due to the support. So in this case, at this beam, at x equals 0, all right, sorry, I should have drawn Lx and then L. At x equals 0, y double prime equals 0, right, from these conditions. And at x equals 0, I get that y is also equal to 0. At the same time, this is also a simple support, or simply supported. So I'm going to say that at x equals L, y double prime, or the moment, is equal to 0. And then at x equals L, the deformation, or the displacement, is also equal to 0. So those are our boundary conditions that we can use. Now, note that I technically use this as one boundary condition, the Q, right, from this part here. I've got a second one, a third one, a fourth one, and a fifth one. And I had 5 constants, right? So I had y is equal to c1 plus c2x plus c3 x squared plus c4 x cubed plus c5 x to the fourth. So I need, if I have 5 constants, I need 5 separate boundary conditions. To solve. It's kind of like having equations to solve for the indeterminacy. Or using the equations of equilibrium to solve for a structure, right? You need as many equations as you have unknowns. We need as many boundary conditions as we have constants. So going through this, if we plug in x equals 0 and y equals 0, then all these terms cancel out because we plugged in x equals 0. So c1 and y, all we did was take the function y, the whole function, and plug in x equals 0 and y equals 0 and c1 equals 0. At x equals 0, y double prime equals 0. So I just went up and I grabbed the double prime and I brought down and made x equals 0 and y equals 0. Then it also gives us that c3 equals 0. Okay, this should be x equals L. So at x equals L, then our double prime is equal to 0. And I did it this way on purpose. So our y double prime actually looks like this. 2c3 plus 6c4 x plus 12 c5 x squared equals 0. Well, I have c3, right? That equals 0. So that's why there's no c3 term. c4 we haven't solved yet, and I do have c5. c5 was equal to negative q over 24 ei. So if I plug in x equals L, then I get 6 c4L plus 12 c5L squared. And then I'm going to plug in that c5. And all I have to do is rearrange it. And then I get that c4 is equal to c4 is equal to ql over 12 ei. So I'm just doing basic math here and writing it out. If I put in at x equals L, then y equals 0. Now, because I have more terms in the y, it's sometimes easier to solve for the shorter term, or whatever one you can isolate only one variable in. So I kind of did this one. I did this one y first and then y double prime. Now I'm doing y double prime and then y because y has more terms. But it's basically simplified down to this. So C2 times L plus C4, which we just solved, so I plug that in, times L cubed minus Q over 24 EI times L to the fourth equals 0. It factored out, expanded, common denominator is blah, blah, blah. I get that C4 is equal to negative QL cubed over 24 EI. So all I do is I plug those back into the formula for y, like replacing all the constants, some of them being 0, like C1, C3 is 0. So I've got C1, C3, C2, and C4. Going back up, C1, C2, C3, C4, C5. I've solved for all those. And the answer is this thing here. If I look at the back of the Hebler, the textbook, this is the equation that it gives us for our beam table for a uniformly distributed load. They call it W in the back of the book, and I left it that way on purpose, for any point X along the beam. a simply supported uniformly distributed beam, or simply supported beam with a uniformly distributed load. It looks like it's in this form. However, if you factor it out, this is what you end up with. And if you substitute Q and if you substitute out Q for W, and you compare the terms, so my fourth term, I think there was supposed to be an L here that I missed. I'll have to double check that. I think there was an L term that I missed there. Now when I wrote it out. Maybe not. Anyway, if you check the terms, it should look exactly the same. So I've got negative Q over Q, it should be L. QL over 24 EI. Sorry, I made that a mess. Let's do this without making it a mess. So yes, there should be a Q term. I just typed in the equation wrong. If you look at the fourth X term, I've got QL over 24 EI negative is negative here, negative X to the fourth. I've got WL times X to the third, so WL times X to the third over 12 EI, and that's a positive. And then I've got, did I do something wrong here again? My X term. I gotta double check something here. C5 or C2. I did a plus or minus wrong here somewhere. I think I copied this one down wrong, I'm sure. But anyway, if we compare it to the textbook, we get the same answer, which I should have copied it down properly, but I didn't. Anyway, we get the same answer, and that's how basically what our beam tables are for. The only thing with the beam tables is they're only for certain loading cases. When we can use this method to come up with any sort of loading case. So we can say that if we have a simply supported cantilever with a Q at this point, and we have a point load here and an applied moment here, we can still use this method to come up with the deformation at any given point along X. So Y at X is equal to whatever. And we will go through that. Maybe not something this complicated, but we're going to go through more examples later. I'm going to fix the notes and repost them, so forget about that. It does equal the same thing. I don't know why I messed something up there, but just trust me for now that it does work out. That's all I have for this lecture. So I will see you all on Friday. And yeah, we'll pick this class back up on Friday, but I'll see you tomorrow for CE 303. Have a good day.